Hi, my name is Alfonso Campos, and today we'll explain the experiment of the standing sound waves. The objective of this experiment is to get the speed of sound. First of all, we need to understand how a wave of sound behaves. There are two types of waves, a transversal wave and a longitudinal wave. A longitudinal wave is what the more common waves are, for example, the waves of the ocean, on which the particles move perpendicular, in this case up and down, to the wave, which in this case moves horizontal. On a transversal wave is the opposite. Both the particles and the wave move in the same direction. Air is a type of transversal wave. But instead of the particles moving, is the regions on which there is more pressure. Therefore, there is more particles in specific regions. In the air, when sound is produced, there are regions which have a higher pressure, here shown in blue, than other regions which have a lower pressure on white. This pressure, these parts of more pressure, move alongside the wave. Here it's important to know that the wavelength is defined by the distance between the high pressure regions. Okay, so in order to get the speed of sound, we're going to use Conn's tube, which is a tube that is shown in the image that has one side closed and another side open. This type of tube can actually create a reflection and therefore a standing wave inside of it. But this is different than another type of tube that is very common, which is that has both closed sides. When a tube has both closed sides, both extremes act as a node. On the center, there are all the antinodes of the standing wave. In the case of a Conn's tube, as the here on the right side is open, it's not a node, it's an antinode. This means that we cannot have all the same harmonics we have on a closed tube. Here, only harmonics of odd numbers can appear on the tube. The formula that relates wavelength, the length, and the harmonics of a Conn's tube is this one, on which the wavelength of the wave is 4 times the length of the tube divided by the harmonic number. Remember, the harmonic number can only be odd numbers. If we replaced this formula with the formula of frequency, which is equal to velocity divided by wavelength, we actually get that frequency is equal to the harmonic number times the velocity of the wave divided by 4 times the length. In the case of sound, the velocity is the velocity of sound, which is what we're going to try to calculate. Therefore, we need the frequency, the harmonic number, and the length of the tube. Here's how the experiment is set up. We connect a computer with a Pascal program to this machine and this long tube. What this whole setup does is that we have here a small speaker which is connected to this machine, which controls very precisely what type of frequency, what is the frequency of the sound is going to make. And on the other side, we have a microphone. Now, the tube, as you can see here, can be contracted, can be made smaller, and how the experiment is going to work using this is that when a sound is produced, here on the computer, there's going to be a graph of all the frequencies. And when a frequency, which is specified to calculate, for example, in this case of 500 Hz, when the tube is at the right length, this frequency will reach its maximum peak along this graph. It will start as a small peak on the graph, and as the tube gets longer, it will become a maximum peak, and they will start to get shorter and shorter. And this happens multiple times. This is because when the tube is at that exact length, it applies this formula right here, that frequency is equal to the harmonic number times velocity divided by 4 times the length. It's perfect for this formula, so therefore it's more noticeable, that frequency. This lets us know both the correct length of the tubes that produce this resonance, as well as which harmonic it is, because the first time it happens is the first harmonic, and the second time is the third harmonic. Remember, there are only odd numbers on this type of tube. The next one is the fifth, etc. With this type of setup, we can actually know all of the values we need in order to calculate the velocity. Here is the type of graph that will appear on the monitor. This is actually a fast Fourier transform. What exactly is a fast Fourier transform and how it works is beyond the scope of this video, but basically it takes a normal graph, which is the peak here as the sound wave normalized, versus the time, and converts it into this type of graph, which is the sound wave normalized, versus the frequency. It tells us the frequency that the sound is getting to this microphone. So here's a video of the experiment being made. You will see here more clearly what I mean when I say that it becomes a peak. Here you can see there's a small peak right here at 500 Hz, and as the tube gets longer, it will start to reach a maximum. There is a maximum right there. You saw it became to go down. That was the first harmonic for 500 Hz. There is the third, and then we see a fifth, a seventh, etc. When this becomes a maximum, this part of the graph, we know we have reached a length of the tube that creates the resonance in order to create this maximum peak. So here are our results. We made three types of frequency: 400, 500, and 600 Hz. And we saw how what was the length of the tube at each specific harmonic. Now, as we now know the frequency and the harmonic and the length of the tube, we can start to calculate the velocity using this formula. Frequency equals to velocity divided by 4 times the length divided by n. What we're going to do is graph the frequency as the y-axis and the harmonic as the x-axis. This will give us a linear graph on which the slope is the velocity divided by 4 times the length of the tube. So here are the results. As you can see, we have the 3 graphs for each of the frequencies. It's important to note that on the graph for 400 Hz, there is no uncertainty for the slope, because there are only 2 data points. The slope, the best fit line, will be a line that connects both of those 2 points. In order to get uncertainty, we need to get a deviation for this line, and for that we need at least 3 data points, as seen in the 500 and 600 graph. But as you can see, they are very close to a straight line. So when we get the results of each of these slopes and we calculate them using this formula, remember here the slope represents this value here of the velocity divided by 4 times the length, we get these results. Here are the slopes and its uncertainty for each of the frequencies, and after the calculation we get these velocities: 342, 336, and 341 meters per second respectively. The uncertainties for each one were calculated using this image right here, this calculation. As you can see, velocity is equal to 4 times the frequency times the slope. We can factorize the 4 as it's a constant, right here, and the rest will be calculated using the formula of using the uncertainties times its derivative squared, both of them, sum them, and then take the square root. As it's just a multiplication, as the 4 was factorized, the derivative of the slope was just the frequency, and the derivative of the frequency was just the slope. So therefore we have this formula of 4 times the square root of the uncertainty for the frequency times the slope squared, plus the uncertainty of the slope times the frequency squared. This is how we got these 3 uncertainties. They differ as both the slope and the frequency of each were different. Then we take their average. Right here it was 340 meters per second, and its uncertainty was calculated using the formula for uncertainty of average, which is the standard deviation between these 3 values divided by the square root of number of values, in this case 3. So now we need to compare this to the theoretical velocity of the speed of sound. The Iowa State University says that the velocity actually depends on the temperature of the air. It's 331 meters per second plus 0.6 meters per second for each centigrade grade, it increases from 0 degrees. So if temperature is around 20 degrees Celsius, which is around the ambient temperature, this means that the velocity of sound will be around 331 meters per second plus 12 meters per second, which gives around 343 meters per second. The actual theoretical velocity depends on the actual temperature, but 20 degrees Celsius is around the average ambient temperature for most enclosed buildings. So that's why we took 20 degrees Celsius as the temperature. So here is our results. When we compare them, we got the error for each of the calculations. But what's important is that we take the average of all of those, which would mean taking the average of 340 and comparing to the theoretical value of 343. This gives us an error of 2.9 meters per second, which is actually 0.845% of error. This is really low. Therefore, we can say that we successfully got the speed of sound using this experiment, which is actually kind of surprising. As you saw, we only use 2 values for the 400 frequency and 3 for the 500 and 600 hertz of frequency. There's a very small amount of values, and when there's less values, it's more probable that a random error will occur, affecting our results further from the theoretical value. But even with so low results, we got very close to the actual value. So I will say that this is a very good way to calculate the speed of sound. Here's the reference for the theoretical speed of sound we got. The link is also in the description if you want to check it out. And thank you for watching.